Now, one of you guys need to answer it since there's two Daisies in the class. Don't be shy. Daisy, Daisy, Daisy G, Daisy J. Okay, then we'll try the Dianas. What was that?
Does it not dissolve?
It does not dissolve. Excellent. That makes sense, right? So we know a weak acid isn't going to dissolve. So that means it's going to stay together. So an example of a strong acid was hydrochloric acid, HCl. It dissolves into its ions. And so when we talk about major species, the major species is the one that is the most abundant in that solution. So the ions are going to be more abundant in solution than the hydrochloric acid together. Okay. Now, hydrofluoric acid, we kind of talked about hydrofluoric acid. Hydrofluoric acid is a weak acid. The reason why it's a weak acid is because the fluorine is very, very strong in terms of its electronegativity. It doesn't let hydrogen go. It's like, nope, you're mine. You're not leaving me, right? You can't leave. You can't go to the bathroom or anything like that. So it keeps it in contact. Because of that, it doesn't separate, or when it does separate, there's very, very little of it that's separated. Majority of it is going to be together as hydrofluoric acid instead of the ions broken up into its ionic form. Okay, are you guys good?
Yes.
Okay, so let me tell you a little bit more about acids here. Okay, so these are some of the 7 strong acids. So a general rule about acids, if it ends with IC, it's typically a strong acid, except for hydrofluoric acid. If it ends with OUS, it's typically a weak acid. And if it has carbon in it, it's always a weak acid. Okay, did you guys get that down?
Yes.
Okay. So if it ends, if the acid, like nitric acid, IC, strong acid. Sulfuric acid, strong acid. Hydrochloric acid, strong acid. Hydrobromic acid, strong acid. Hydroiodonic acid, strong acid. Chloric acid, strong acid. Perchloric acid, strong acid. Okay.
You said it.
So
Which one did you say was all of them are strong acids except which one?
Hydrofluoric.
Okay.
we know that hydrofluoric is a weak acid.
Why does it end in IC then?
Well, because it obeys that rule. The only reason that it's weak is because it's fluorine. Fluorine is such a strong electronegativity. It won't let it go.
Oh, okay.
So it's just one of the exceptions. So any acid that has carbon in it. It's going to be weak. Okay. So that's like lactic acid, acetic acid, let's see, or carbonic acid. All of those are going to be weak acids because they have carbon in it. Okay. Okay, so let's test this out. Write the formula of the major species in solution of nitrous acid and chloric acid. Okay, so we want to write down what the major species is. So let's just start simply. Let's see if we can write the chemical equation for nitrous acid. So what is the chemical formula for nitrous acid? And then what would it break down to if it broke down into ions?
Is it nitrogen?
HNO3.
HNO3 is the chemical formula. Okay. Is it NO3 or NO? Is it NO3?
NO2? Or would it be NO2?
NO2. And then we need to put aqueous because acids are going to be in water.
Acid.
Okay, so is this nitrous, OUS? Is that going to be a strong acid or is it going to be a weak acid?
Weak.
First off,
Weak.
it's going to be a weak acid. Right? So that basically means that you're going to have, this arrow is going to be much bigger than this arrow, meaning that the majority of what you see in solution is going to be this guy together rather than its ions. That hydronium ion. Okay. Okay, piece of cake?
Yeah.
Okay, so this is the major species. Major species is going to be boxed. Okay, now hydrochloric acid, not hydrochloric, chloric acid. What is the chemical formula for chloric acid?
HC102. Or HClO3.
Okay, HClO3. Is this guy going to be a strong acid or is it going to be a weak acid?
Chloric is strong.
Okay, so what's going to happen with the strong acid?
It's going to point to it with a longer arrow.
Okay,
Aqueous.
are we going to point towards it or is it going to be pointed towards the other?
I mean,
direction?
opposite way.
Okay, so we're going to be producing more of the ions. So what ions am I going to get?
The hydrogen and the chlorine
Okay,
and the oxygen.
a hydrogen, a chlorine, and an oxygen?
I mean, just hydrogen. And the ClO3.
Okay. Okay, you're going to break up into the ionic forms. So you're going to have your polyatomic ion and your hydronium ion. Okay, and then who's going to be the majority? It's going to be the major species. The ions or the acid?
Acid.
Ions.
Oh wait, ions. Sorry for this one, ions.
Yep, it's the ions. Okay, because it's a strong acid. It's going
Yeah,
to
strong.
dissociate, right?
Yeah.
Okay, you guys get that?
Yeah. It's
Yeah.
interesting.
Okay, so up until this point, we've been writing everything in terms of the conventional equation. I'm going to actually show you what happens in the case of ionic compounds that are in solution. And we're going to show you how to write the total ionic equation. Okay, so what happens to salt when you put it in water?
Dissolves.
And it dissolves into what?
Just
Salt
dissolves.
water.
Hot water.
So is there still remnants of that salt in there? Or is it just
Yes.
gradually
Yeah,
disappears and
there's still
becomes
some at the
water?
bottom.
Yes, there's some at the bottom.
Some becomes water and some doesn't.
It would
Could be floating around in warm water if you stir it up.
it's still
Okay.
sodium
So
in
if,
the
you just
water.
if we put a little bit of salt in water, will there be anything at the bottom?
Yes, once it's
Not if you
settled.
put a little bit.
Okay, I want you guys to do me a favor. All you guys have salt, right?
Yeah.
Go to your kitchen, get a hot, turn on your faucet right now. Everybody turn your faucet, get a cup, and then all I want you to do is put in a pinch of salt in that water.
Okay,
Just a
I did
bit.
it. It doesn't work. It doesn't work.
What do you mean by it doesn't work?
It
The
doesn't
water doesn't
dissolve.
work?
I mean, it doesn't go down to the bottom of the glass. I just did it right now.
Uh-huh.
Mhm.
So why doesn't it go down to the bottom of the glass? Now I want you to think about that.
It's suspending in aqua.
So I put some salt and mine did go down. Why?
You said it went down?
Yeah, I put hot water in a cup and then I put a little bit of salt and then it sunk to the bottom and then some's kind of like coming up, but the majority of it is in the bottom.
Maybe the mass of the molecules or something. Maybe it's heavier than the water.
I don't know why. The majority was in the bottom.
Yeah, it is because of the mass.
Or maybe my water's not hot enough. I don't know. I mean, it didn't dissolve, but it's still there.
The density.
Did we lose Dr. Henry?
Probably went to go get a water in a cup.
Yeah, he's gonna show us.
So I don't use like regular salt. I don't know if that has to do with anything.
No, it's the density. It's once you add the salt to the water, the salt's heavier, so it's gonna sink.
Okay. Are you guys here?
Yeah,
Yeah.
you were gone for so long. I was thirsty. I drank that salt water.
Excellent. How do you taste?
Salty.
Like the,
Salty.
like the ocean.
Okay. So what happens is it breaks up into its ionic components. Just like those acids, they split up. Okay, because we know that water is a home wrecker, right? Water gets in between the sodium and the chloride, and it keeps it in suspension. So long as you don't have too much salt, and you have enough water molecules able to, you're going to keep it separated. Okay?
So where should the water stay? At the bottom or at the top?
What was that?
So should the water stay at the top or at the bottom? Because mine's not.
So if you put a lot of salt in it, then what's going to happen? The water is just going to go through between it. Over time, you're able to dissolve that salt, but there has to be enough water molecules. So the water is going to be all over, and the salt is going to be all over. As you mix it, it's going to be all over, right? And you can let it sit for a long time until the water evaporates. That salt won't come together unless if there's water there. If there isn't any water there, then the salt does come back together. Long as there's water there, it's going to keep it separated. Make sense?
Yes. Thank you.
Okay, so all ionic compounds that are in aqueous solutions, if they're able to be dissolved or if they're soluble, they're going to break down into their ionic components. So here we have lead 2. So lead 2 is 2 plus. It's an aqueous solution. Now, when they break up, in this case, we have a lead 2 nitrate. When lead 2 nitrate breaks up, nitrate is free to roam, right? So it's not going to be connected to the other nitrate. The only thing that's keeping it connected is that plus charge of the lead, okay? So then, in that case, you're going to treat these guys as 2 individual nitrates. Okay, now sodium chloride. What's going to happen with the sodium chloride? What did we just discuss? What does water do?
It gets in between them.
Dissolves
Okay.
it.
So it breaks them up, right? So we know that sodium has what charge associated with it?
Plus.
And chlorine, the chloride ion,
-1.
1.
right? Okay. Now here's a very important thing. So you may want to definitely take a moment to write this down. Now, when you have a solid, liquid, or gas being formed, then you leave it alone. You don't do anything to it. You don't break it down, or you don't break it apart. It stays together. So in this case, lead to chloride is going to stay together because it's a solid. So what's going to happen with the sodium nitrate? What happened to the lead nitrate on the other side?
I guess I'm still stuck on what you said. So solid, liquid, gas, we never break it up. So the only one that would be broken up would be acid.
No, the only
What's
thing
the
that
other
would be
one?
broken up is things that have aqueous, AQ.
AQ, that's what I mean, sorry. Yeah.
Yeah.
AQ. Okay. And then what happened to the other side?
So what's happening to the sodium nitrate?
It's gonna get broken up.
It's going to get broken up.
Yeah.
Okay, questions, concerns, Ash? Okay. So how many of you guys have gone to a party and or gone to the party with somebody and you get to the party and the person that you with just sit there and stands there and watch everybody else?
Yeah, that's boring.
Are you the only one? Heather's the only person that's gone to a party and that's happened to?
No.
Anybody else social?
Yes.
Well,
No.
obviously, this class, I don't know. They don't know how to talk. They don't know how to. Okay. We obviously know
Okay,
they
I
don't
admit.
party.
We've been to them.
Yeah, I mean, I admit I am that person. No, I'm just playing. I'm just playing.
Okay. So you guys know that person, right? So
Right.
here we have what we call spectators. A spectator is just somebody who goes to a party and they watch everybody else have a good time, right? They're spectators. Okay. So in chemistry, we have spectators as well. So a spectator is going to be that chemical compound or that chemical element that is going to be exactly the same on both sides of the equation. Okay, and they have to be exactly the same on both sides of the equation. Okay, so can you guys help me identify the spectators?
Yeah. It's gonna be the 2NO3 aqueous.
Okay, what is that called?
Nitrate.
Nitrate. That's right. It's called nitrate. Nitrate.
Had a frog in my throat. I couldn't get it out.
Nitrate.
Nitrate.
Okay, what else?
And the
Wait, what was the question? I'm sorry.
2Na
So the question was,
sodium.
can you help me identify the spectators? A spectator is the ion or the substance that is exactly the same on both sides of the equation.
2 sodium with 2Na aqueous.
Okay. Okay, so my two spectators were the nitrate and the sodium ion. Okay, so when we determine the net ionic equation, we just remove the spectator.
So we remove them?
Yep.
And then the party continues. It's more
That's
lively.
right. So the way I like to look at it is, right? So each of them brought somebody to the party. They did nothing. They just sat around and watched other people do anything. And the two people that they brought hooked up together. They left the party together.
Woo! It's drama.
Chemistry is all about drama. Didn't you realize that?
Yeah, after being in this class, I did.
Okay, and it makes sense if you look at it, right? What happened? So we had lead to nitrate come to the party together. Water splits them up. And then sodium chloride comes to the party together. Water splits them up. And then they hook up together. Lead to chloride hook up together. And they're a good couple. They stick together, right? They form that solid. Okay, so that is the net ionic equation. Piece of cake?
No.
So they form that solid.
Yeah.
Will they ever form anything else other than solid?
No, they will only form a solid together, right? Because what it is, all you're doing is switching partners, right? So you have that swinger reaction that's going on. But there's certain things that when they come together, water can't break them up, or it takes a whole lot of water to do it. And sometimes we're limited by that, okay? And that's determined by the solubility of the compound, okay? Certain things are more soluble, meaning that they're able to be dissolved in water. Other things are insoluble, meaning that they can't be dissolved in water, okay? So what happens when these guys come together? Lead chloride, it's really hard to get it to dissolve in water. The only way that you can do that is by adding a whole lot of energy, to that. And so it'll form a solid under normal conditions. Does it make sense?
Definitely.
Okay, let's see those skills now. Okay, so when you're writing the net ionic equation, the first thing that you always want to do is you want to write down the conventional equation. You want to make sure that you have every chemical formula correct. You want to make sure that you include the state symbols. So is it aqueous? Is it a gas? Is it a liquid? Is it solid? Then you want to make sure that you have it totally balanced, okay? And then you go through and you determine the total ionic equation. Anything that is aqueous is able to be broken up, except when you're talking about acids. All acids are going to be aqueous. However, strong acids are going to be able to be broken up, where weak acids aren't, okay? Does that make sense?
Yeah, Dr. Henry, I have a question.
Yep.
So, like in the first one, the PbNO3, how come you can't just take all of those aqueous solutions out of there?
Well, because the aqueous solution, okay, so you're not getting rid of them, right? Because you need the lead and the chlorine are what is going to be reacting. That's what you're interested in, right? So when you're putting those chemicals together, you're trying to make lead chloride. So if you take them all out of there, right, then you're not going to have any reaction. The whole purpose of it is to have a reaction.
Are you ready to come in, or you're going to keep crying?
Does that make sense?
Yeah, except for
Okay, stop crying.
I think I was getting stuck on lead being aqueous.
Lead, it's the lead ion that's aqueous. It's not the lead itself, right? And what that means, it's not that it's aqueous. That means that it's in water, right? The ion itself is in water, and the water is keeping it in solution.
Okay.
Okay. So
Like the
kind of
salt
like,
in the water. It's still there.
yeah. Yeah,
Okay.
the only thing you don't see it because, it'll be a clear substance. I think lead is a yellowish substance. It's gonna be suspended in water. It's gonna be kept in suspension in water. So you're using the water to sit there and help facilitate the reaction, right? That's why we put stuff in water, right? So like for instance, saline solution, right? So when patients are getting injected with saline solution, what are they getting injected with?
Salt water?
Salt
Salt
water.
water, right? So you're trying to get the ions because the ions are responsible for the polarity of the membrane and things like that in your body. So you need the ion. You don't need sodium, right? You don't need sodium metal. So we're not putting sodium metal in there. We're putting the sodium ion, right? And they're going to behave differently than the metal would, right? Does that make sense?
Yeah, but how did we know that lead was not a spectator?
Well, we know that lead wasn't a spectator because lead wasn't on both sides of the equation in the same form, right? So we take a look at, here's the total ionic equation. Lead is Pb2+ here, and then here it's connected with chlorine. So it's not going to be a spectator. Spectator means it has to be exactly the same on both sides of the equation, right? This guy here, which is screwed up. This guy is going to be the same on both sides. So that guy is going to be a spectator. And this guy is going to be a spectator because it's the same on both sides. Right?
Okay.
Both in the ionic form. So literally, they're that guy that literally comes to the party and does nothing, right? Where lead is going to hook up with chloride.
Okay.
Okay.
Mhm.
Okay, let's see those skills now. Okay. Let's see. The other thing that you want to always remember to do is that you want to make sure that you've reduced your coefficients to the lowest term possible, right? So you want to make sure if it's all divisible by 2, you want to make sure you've already divided by 2. In most cases, if your equation is balanced correctly in the first place, it usually works out pretty well. Usually, not always. Okay. When a strip of magnesium metal is placed in iron 3 chloride solution, a magnesium chloride solution results, and solid iron also forms. Develop the net ionic equation for the reaction. So the first thing that we're going to do is write the conventional equation. So what would be the conventional equation for this reaction?
Magnesium is
Okay, so what is the symbol for magnesium?
Mg. Is it just
Got it.
one? If it doesn't say anything different?
Yeah, Mg. So, well, no, we've got to figure that out. But first, we need to make sure that we have the right chemical formula. So it's
What do we-
Mg. Is it
Plus-
solid, liquid, or gas?
Solid.
Okay.
That's Fe. That's Fe is iron.
CL3.
15 years later.
From 15 years ago. You better frame it. I don't do it for free.
What? What's going on over there?
You're not on mute.
Okay, so we have, is that solid, liquid, or gas, or aqueous?
Aqueous.
And what are we going to make?
We're going to make a solution of
Okay, what solution?
magnesium chloride.
Okay, chemical formula.
Would be MgCl3.
Is it MgCl3? What is the charge on magnesium?
Plus 2.
So if it's +2, how many chlorines do I need to balance it out?
-2.
What was that? I'm sorry, I couldn't hear you.
I said, if it's +2, how many chlorines do I need to balance it out?
2.
Okay. And we know that's aqueous because it's a solution. And then what are we making? What is the other thing?
Fe,
Okay.
iron.
Solid, liquid, or gas?
Solid.
Okay. Okay. Is it balanced?
I'm thinking maybe not.
Okay.
Your question.
No.
Let's confirm that. So I'm going to write them all out.
No, because there's one, we need another CL on the product side.
Okay. So we have 3 here and 2 here.
Mm-hmm.
Okay. And then everything else has 1. Is that right? Okay. So what do we need to do to balance it?
Need another CL.
Okay. So how am I going to get another CL?
You're gonna put
3.
two in front of it, the MgCl.
2 in front of here. So then that gives me 4 CLs now. And then this gives me 2.
So and then you could, oh, never mind.
3.
I'm really bad at this.
3. What was that?
3
Put a 3 where?
in front of MgCl2.
Okay.
Let's make
So
that
put
6.
3 here.
Yeah.
Okay, so we put a 3 here. So now we got 6. We have
Mhm.
3.
You
Let's
put
put
3.
2 in front of FeCl3.
Okay, so then that gives me 6. And this gives me 2.
And then you put 3 in front of the Mg.
Okay,
And a 2 in front of iron on the product side.
okay.
What do you know?
That looks like it's balanced. Okay. Okay, so that's the first part. Now the next part. We want the total ionic equation.
Oh. 3Mg.
Okay. So we'll have Mg, 3Mg.
Mm-hmm. And 2 Fe solids.
2 Fe.
Mm-hmm.
What is the state of that Fe?
Positive. Oh, S, solid. It's
Are you
positive
sure?
solid.
Are you
The
sure?
other one. I meant the other Fe at the end of it.
Oh, you're talking about over here.
Yeah.
Well, we need to write the full equation first, right?
Oh, okay.
Start off with the reactant part.
It'll be
Don't be too
AQ. Aqueous.
AQ, is there going to be a charge associated with that Fe?
Mm-hmm.
What is going to be the charge?
Oh, no, there isn't.
Are you sure? Because what happens when you separate them? Are they going to be charged? You have an ionic
Positive.
compound. It's going to be positive. What type of positive? 1, 2, 3, 4, 5,
Positive
6.
1?
Are you sure?
No. Positive.
2?
3.
No, 3. 3.
Okay, it's going to be a positive 3. Why is it a positive 3?
Because there's 3 chlorine.
Chlorines.
Chlorines.
Because there's 3 chlorines, and we always know chlorine is always going to be the same thing. It's always going to be a -1. Okay, so then how many -1 chlorines do I have now?
2.
I'm going to write what you just told me.
I don't know where
So
we're at.
this is what you just told me, right? Now, you just told me that they take 3 chlorines. Now, what the hell happened to all the other chlorines?
That's what I want to know. I want to know the same thing.
There's 3.
There's 3, but there's 2 times that, right?
So 6.
Because it's a big total of 6, right?
They all left the party.
That's right. Remember, they're splitting up now. Because the thing that's holding it together, those negative charges together, is that positive charge. If they're splitting up, you no longer have that positive charge holding it. Does that make sense?
Yes.
Okay, so then on the other side, what's going to happen?
You have 3 magnesium.
Is it going to have a charge?
Yes.
Yeah.
Okay, what is going to be the charge?
Positive.
Positive 2.
2.
Because we know that magnesium is group 2. It's always going to be positive 2. Okay. And
Chloride is
Cl.
negative.
Cl minus. How many?
6.
Yeah.
Yeah, 6.
Good job. And
2 Fe.
2 Fe. Solid.
okay, so it's going to be really important to keep track of your charges. So you want to make sure you have that down, really well. Okay, so here's the next part. So who are the spectators?
F.
The aqueous.
The awkward ones. Let's find them.
Q.
Let's find them and kick them out of the party.
This chlorides.
Chlorides. Okay, so the chlorides are going to be spectators.
Aren't like all of them spectators?
Nope.
Actually, no, except the Fes.
So
And the 3 Mgs.
One's aqueous, one's solid.
Oh yeah, you're right. I didn't see that.
That's right. So this guy is a solid. It has no charge. So they are not exactly the same. They're different, right?
Yeah, they're
This-
different.
They're different. Yeah.
They're different.
Yeah, this one, they're different because, well, magnesium solid is a metal for one thing. And then this guy is an ion. It's an ion in solution. This guy is kind of uppity. He has his electron. It got rid of the electrons that it didn't need, right? So it's a little uppity. It's happy, right? This guy isn't quite so happy yet, Okay, so they're different. You need to make sure that you understand that. So that solid is going to be different than that aqueous solution. Okay.
So we're good.
So our net ionic equation is going to be what?
So if there's a aqueous in the solid of the magnesium, you keep both of them?
Yep.
Mhm.
Okay.
You only get rid of things that are exactly the same on both sides.
Pairs,
Identical.
like pairs. Okay.
It would be 3 Mg solid plus
Okay.
2 Fe, 3 plus aqueous.
Okay.
And then the other side, it's going to be 3 Mg, 2 plus aqueous plus 2 Fe solid.
That is great. Good job. Is that Diana?
Yes.
High five. Okay. Piece of cake.
Yeah.
So anytime that you see aqueous, the compound in there, if you can separate, it's going to separate, right? So if it's an ionic compound, it's going to separate. An acid, it's going to separate. Okay. And when we talk about separate, it's going to form the ions that we know. It's going to form either that, if it's an acid, that polyatomic ion and H plus. If it's an ionic compound, it's going to form that metal and that non-metal independently. And you need to keep track of the charges. Okay.
Okay.
Okay, so let's see. We're gonna see if you guys got it because I keep saying it. I want to see this improvement because I want to start seeing other people starting to talk too.
Got it.
Okay. Okay. Actually, before we start with that, go back a little bit. Let me explain one more thing to you. We know that you guys have the capacity of learning so much. So
Sponges.
I know, exactly. I need to get it while it's still right? And then, okay, so if we take a look at this, the charge on this magnesium is what? The solid. What is going to be the charge? Since it's an element. All elements are what charged?
It's a plus positive 2.
All elements are what charge? Everything on the periodic table has what charge associated with it?
0.
0. So this guy has a 0 charge. All elements, because it's balanced with the number of electrons and the number of protons is totally balanced. So it has a total charge of 0. Okay. It wants to be an ion. And when it wants to be an ion, it's going to try to become +2 charge, which means it's an ion, right? So if you have a metal, it has a neutral charge. If you have an element, it's going to have a charge associated. It's going to have a 0 charge. So the magnesium ion has what charge associated?
It's 2+.
Okay, so it's a 2+. So if I'm going from a 0 to a 2+, what am I doing? Am I gaining electrons or am I losing electrons?
Losing.
Losing.
I'm losing. Okay, so this guy is losing. Okay, now the iron 3 ion is going from iron 3+ to a 0 charge. So it's going from a +3 to 0. Is that gaining electrons or is that losing electrons?
You're gaining.
Okay, so when electrons are being lost, it's called oxidation. Or I like to say Leo. When electrons are being gained, it's called reduction.
So what do you call that one?
Grr. Okay, so we would say magnesium, the magnesium metal is being oxidized and the iron 3 ion is being reduced. Okay. And so, that, if you notice, one is losing an electron and the other guy is gaining an electron. So you're just getting a transfer of electron for this reaction. So electrons are just being transferred from one metal to the other metal, or to the other metal ion. Okay, and this process is called, it's a special type of reaction. It's called an oxidation reduction reaction. Okay, that being said, here's another problem. Okay, it says an iron nail is dropped in a solution of hydrochloric acid. So you guys have to write the chemical equation for an iron nail being dropped in a solution of hydrochloric acid. Okay, so what is the first thing that I need to do?
Write your equation out for the nail and the hydrochloric acid.
Okay,
Mention
so you want to help me out with that?
Fe.
Fe, solid, liquid, gas, or aqueous?
Solid.
To make everything easier, couldn't we just put rust, that it would rust?
No, this is chemistry. If you keep that up, we'll make you talk chemistry all the time. Everything that you're talking about has to give me, you have to give me the chemical formula for every reaction that is happening.
Okay.
Breathing, so you have to tell me cellular respiration. And okay, so what is the solution? A solution of hydrochloric acid. So we're dropping a nail in the solution of hydrochloric acid.
Oh, is it HCl?
Hydrochloric acid. Come on.
HCl.
HCl.
Ick.
Solid, liquid, gas, or aqueous. It's aqueous, that's right. Okay, so this is often a single replacement. So that's exchanging the old girlfriend for the new girlfriend. So who's being released?
Hydrogen.
Hydrogen. And we know if we have hydrogen by itself, it has to be
2.
so H2. Diatomic. And then anytime that you have a reaction with a transitional metal, most transitional metals, like where you have a single replacement reaction, most transitional metals will have a +2 charge associated. Okay, except for silver and aluminum. Aluminum is +3, silver is +1. Okay, so this guy's gonna have a +2 charge associated with the iron. So what is going to be the chemical formula for the iron chloride? What is going to be the charge of the iron again?
2.
2. So it's going to be iron 2 chloride. So how many chlorides am I going to need to balance out that +2 charge?
2.
2.
Okay, so it'll be Cl2. Okay, and it's going to be aqueous. Okay, so what do I need to do for the total ionic equation? Oh, is this balanced first off?
No.
What do I need to do to balance it?
You need another H on the reactant side.
Okay, so how do I get it so that there's another H on the reactant side?
You put a 2.
Okay. So now is it balanced?
Yes.
Okay. So we have a balanced equation. So now what are we going to do? I heard somebody say Fe. So we don't do anything to solids, liquids, or gas, so we just drop those guys down. Okay, so what happens in the aqueous solutions?
Does it stay the same?
It's aqueous. It isn't going to stay the same. Anytime you see aqueous, what happens? What happens to a strong acid? Isn't hydrochloric acid a strong acid?
Dissolves?
It separates,
It
right?
separates. That's what I meant. Sorry.
Oh, I know what you meant. So it separates. Okay, so then what is it going to separate to?
2H2Cl.
2H plus 2Cl. Now don't forget the charges. And the charge on Cl is?
Negative.
There's 2 of them. Okay, on the other side. What's happening with the iron 2 chloride?
Separates.
It separates. Okay, so I'm gonna get
Fe
2.
and Cl2.
is it Cl2 or 2Cl?
2Cl, sorry.
That's right.
And it's a negative charge.
Okay. Any spectators?
2Cl on both sides.
Okay, so then our net ionic equation is going to be
Fe solid plus 2H aqueous.
that's right.
H2 gas on the other side. Plus Fe2 aqueous.
Good job. Okay, now here's the hard question. Who's being oxidized and who's being reduced? So we're going from in the case of the iron, it goes from a 0 to a +2,
Then it's losing the electron.
losing this electron. So then that would be Leo. So then by default,
Gaining.
be gaining an electron.
Skur.
Right. Piece of cake.
Mhm.
So.
And we're almost getting to the good stuff, right? Okay. Okay.
Oh, this is where our next lab is going to be, huh? With those little test strips.
No, I couldn't get everything that I needed for your lab.
Oh.
I was trying though. You know, I got your aluminum and there's a couple of things that I wanted to add it to it, but we couldn't send it out.
Mhm.
So. Okay. Okay, let's see. So we have a reaction between zinc and a solution of copper to nitrate. So what is going to be the chemical equation?
A Zn.
Okay. Solid, liquid, gas, or aqueous?
Liquid. And I'm
Zn-
sorry, it's a solid.
Okay.
I don't know what I'm thinking.
Evelyn, copper to nitrate.
Cu.
NO3 negative.
NO3. Now remember we're writing the conventional equation first. So it's NO3 negative, but how many of those am I going to need to balance out that copper?
2.
2. I need 2 of them. So the overall, there's not going to be a charge associated with it when we're writing out the conventional. And that's going to make? Remember, you're replacing the old girlfriend for the new girlfriend.
Which one's the new girlfriend? The polyatomic?
Okay.
Zn.
Put it like this. You have a metal. Is a metal going to replace a metal, or is a metal going to replace a non?
They want
Metal-
something different?
Metal?
Metal is going to replace a metal. So if I'm replacing the old girlfriend with the new girlfriend, I'm not going to replace her with Tommy, who's a male, right?
Maybe.
I might, with under different circumstances, but I'm replacing the old one for the new one, right? So
Would be zinc.
Yeah.
then, and then what did I say about transitional metals? All transitional metals are going to be a what charge?
Yeah.
Except for silver and aluminum.
Oh,
Positive?
positive, yeah.
Positive what?
2?
2.
Positive 2. So all of them are going to be positive 2 charge. So then how many nitrates am I going to need to balance out that positive 2 charge that the zinc has now? I'm going to need 2.
2.
That's right. You guys are saying it under your breath. You got to be confident. Hell yeah, it's 2, right? Because I know it has a +2 charge. I know that nitrate has a -1 charge, right? I need that confidence.
Well, I was thinking we already had 2 on there.
Well, we have a +2 charge, so we need those negatives to balance it out, right?
Okay.
We're still working on that conventional. Okay, and so that means that copper is going to be,
Alone.
and it's going to be solid, right?
Solid, yeah.
Okay, so now that we got our conventional equation, is it balanced?
Yes.
Yeah.
It is balanced. Okay, so then since it's balanced, so now I want to find my net ionic equation. I mean, my total ionic equation. Get ahead of myself.
You would separate the aqueous or I don't know how to say it, but the
That's right.
equations, yeah.
The aqueous solutions. That's correct. Okay, so if you separate this guy, we're going to get copper, what? What's the charge?
+2.
Okay. Aqueous. And then how many nitrates are we going to have?
Oh, yeah. 6.
6.
It's
Or, sorry, 2. 2.
2 nitrates, because
Yeah, I
it's
see
a
it.
package deal.
oh, okay.
Mhm. The 2-per.
2
Does
NO3.
that stay in parentheses?
What was that?
Would the nitrate stay in parentheses?
No, you would take it out of parentheses. You just put the 2 in front, right? Because once it's kind of like this kind of magnet. If you have a positive here and you have these 2 things that are connected to that magnet, as soon as you pull that magnet away, those 2 pieces of metal aren't going to be attracted to each other. They're not going to bind together. They're going to be independent.
Oh, okay.
Okay. And then over here, what's going to happen with the zinc? The zinc nitrate
Separates.
separates. What is the charge on the zinc?
2.
+2.
How many nitrates am I going to have?
2.
2. And no 3 negative.
That's right. And then we know that anything that's a solid, liquid, or gas, we're going to leave alone. Okay, who's our spectators?
2
All of
and
them.
03. That's it. It's a wrap.
That's it. That's right. So then my net ionic equation is going to be
ZnS plus Cu2. Zn plus CuS solid.
Okay, piece of cake?
Yes.
Okay. Who's being oxidized? Who's being reduced?
The zinc is being oxidized.
The copper is gaining. Grr.
Okay,
Right, with confidence. Grrr.
that's right.
We're all turning into chemistry lions here.
That's right. Grr.